Hello everyone, I'm Pontus Loviken, and this is a presentation of mine and Nikolas Hemion's work, Online Learning and Planning in High Dimensions with Finite Element Goal Babbling. Before going into any details, I would like to give you a preview of our method so that you will have some kind of intuition about what I'm gonna talk about later. So the main contribution of this paper is that we show how you can combine a goal babbling framework with a Markov decision process planner. So if you see the space here, you have a very high dimensional arm, and goal babbling allows you to very efficiently find an inverse model so that the arm know what posture to use to reach more or less any position within this space. In this case, the arm tries to reach for the blue X. But in many environments, you have to plan your motions. It's not enough to know what posture to use, because in this case, for example, you might know exactly what posture to use to reach the X, but if you try to go directly to this posture, you will just bump into the wall. So what we did was that we segmented this whole space into smaller regions. This allows a higher planner to learn the connectivity between these different regions. So if you want to reach this X, for example, then you first need to go to the region to the left and then down, and then you can go to the X. We have also evaluated how this works for example, different degrees of freedom of the arm, and what happens if you have different kinds of segmentations of this space. I will also talk about the consistency problem, which happens if you can reach the same region in two different ways, but where an average of these two ways would lead to a posture that is not in this region. And I will try to convey to you why this problem occurs when you try to combine a goal babbling framework with an MDP this way. Alright, so in this work we have been looking at behaviors that can arise from task spaces. So a task space is basically some representation space or a sensor space, usually very low dimensional, that you want to control. What is interesting is that if you learn how to use the motors that you are in control over to control these task spaces, then you would have behaviors arise more or less naturally. For example, if you control the head's height over your feet, then to control this parameter from a low value to a high value would make you stand up, and to control it from a high value to a low value will have you lie down, for example. And the displacement, if you control the displacement in the room, it would lead to some kind of locomotion, and to control your hand's position in the room could lead to behaviors such as reaching. Okay, so how can you gain control over a task space provided the motors you're in direct control over? One of the most classical approaches is motor babbling, which it's basically just to try different motor actions out and see what effect this has on the task space. And this is nice because it allows you to potentially find every possible way to do something, but you would also bump into the curse of dimensionality. So the problem is that most robots are very high dimensional. If you try to thoroughly explore this motor space, you have to sample forever before you can learn to do anything at all. An alternative approach is goal babbling. The general idea here is to utilize that the task space is usually very low dimensional. So instead of picking motor actions randomly, you would pick goals randomly in your task space that you try to accomplish. Because you try to sample the task space, which is low dimensional, rather than the motor space, it means that you can use the low dimension of the task space to quickly learn an inverse model. But then the negative thing here is that you would typically only get one solution set. You would only get one way to reach any position. Some examples of goal babbling. So Matthias Rolf et al. Showed that goal babbling can be used to very efficiently learn how to control the end effector position of high-dimensional arms in a two-dimensional case here to the left. But since this method is so sample efficient, you can also use it for real robots, as in the case to the right here, for example. So as far as we know, previous goal babbling frameworks have only looked at situations where you can actually ignore the initial state of the system. This applies, for example, if you're not interested in the trajectories, if you're just interested in sampling a task space efficiently, as in the PhD thesis of Fabien Bonnereau. It also applies in cases where the starting conditions are always the same. So in this work of Sébastien Forestier et al., they showed that an arm can learn many task spaces in parallel. But in this work, the action of the arm would be an extended motion where it would grab for a handle, for example, and then grab for an object. But all of this is just one motion, and after each motion, the whole scene is reset to the original setup again. So in this case, you don't need to consider the starting condition because the starting condition is always the same. Finally, goal babbling can be applied if you have a task space where it's possible to learn an inverse model so that you can go between any two postures directly in this task space. A counterexample to this is in the case when you have walls or obstacles, for example, because in this case it's impossible to find an inverse model that allows you to go directly between any two postures. Before going on, it could be useful with some notation. Throughout this talk, Q will represent the posture of the arm, which is the configuration of joint angles of the arm. And X will denote the end effector position. And then you have a forward kinematic model, which tells you what end effector position you would reach given a specific posture. And then G of X will represent one inverse model, which basically tells you what posture could you use in order to reach the end effector position X. Okay, so the proposed model. The main intuition behind finite element goal babbling is that even though goal babbling is not applicable to this whole task space, it is applicable on a local level. So if we segment the space like this, then we could actually use goal babbling within each such region. In the next step, we would denote each region like this, and then you can abstract each region as a state in an MDP. And this is the higher level planner. So for example, at the level of the planner now, we can see that if we want to go to region S12 and we start in region S8, then we cannot go straight from S8 to S12, but first we need to transition to S7, to S11, to S12. And then when we try to reach different goals within these regions, then we would use the lower level goal babbling framework. So this is an overview. So basically, the MDP will decide which region you want to try next, and it will convey this to the goal babbling framework, which will translate this into a posture that will actually take you there. This is then tried out in the environment, and this will return a new posture and a new end effector position, which can be used to train both the MDP and the goal babbling framework in parallel. So let's have a look at the MDP learning. So first of all, the MDP will use goal states as actions, similar to the options framework, for those of you who are familiar with that. So the action of the MDP is basically just to state what region it wants to reach next. And then it's up to the goal babbling framework to actually take it there. The model that it tries to learn is the probability that the goal babbling framework would successfully bring it from one state S to another state S prime. In order to learn this model, it's using an intrinsic reward that will help the MDP try to put the attention in the areas of the task space where the system can improve the most. And once this model is learned, it can be used to reach more or less any goal states. Okay, so how does the goal babbling framework know what postures to use in order to reach different positions? So in this case, Q is your posture space, your motor space, X is your task space, and the task space have been divided into smaller regions, in this case 3 different regions. And then you have some data points that you have observed previously. Okay, so first of all, we will give one data set to each such region. So let's say that we now want to go to an end effector position somewhere within region S2. Since we already have data here, then we can basically just take this data and make some kind of linear regression, which could give us some first estimates of what Q to try. How about if we try to reach a region that we haven't reached before, like S3? Well, then we can basically just extrapolate from one of the neighbors. Finally, we will add some exploratory noise to allow some exploration in the motor space as well. Okay, now let's talk a little bit about the consistency problem. So, as I said before, the consistency problem occurs if you have two postures that would reach the same region, like here, but where the average of the two postures would not be in the same region. This has two problems basically, and the first one is that you cannot use linear regression anymore, because linear regression will make an average of your previously seen postures. But in this case, this would make the inverse model fail, because you would end up outside of the region. This is however not critical, because you could use other method than linear regression. For example, you could just try to go to the closest neighbor that you have already seen. A more severe problem arises as an interaction between the MDP and the goal babbling framework. And this problem is that each MDP state must behave consistently. So what do I mean by this? Well, at the level of the MDP, each region is seen as a discrete state. And this means that the MDP assumes that the dynamics from this state will be more or less constant no matter where in the state you start. This is, however, not true if you would reach into the region in different ways. So let's say that you can reach into the region S3 in two different ways, in the posture Q1 and in the posture Q2. Then assume that you would reach into the region S4, like you can see here in gray. In this case, it might be so that you could actually go from S3 to S4 if you're using Q2, but you cannot go from S3 to S4 if you're using Q1, because in this case, the arm would probably first reach into region S1. At the level of the MVP, the question is then, what is the probability to transition from S3 to S4? Because now you have this hidden parameter if you're using Q1 or Q2, which gives different probabilities. But this is invisible to the MDP, so this makes it difficult for it to plan. To make it even clearer, assume that you would use one posture in one part of S3 but not in the other. And also that one of these postures allowed transitions to S4 but not to S1, and the other one allows transitions to S1 but not to S4. In this case, it would look at the level of the MDP as it's possible to transition between S1 and S3, and it is also possible to transition between S3 and S4, which would fool the MDP to believe that it's possible to actually go from S1 to S3 to S4. And we know that this isn't true because you have the hidden parameter with different values in S3 in both of these cases. So what we did to solve this is that we will enforce each region to have a consistent inverse model, which would mean that it has to choose one of these ways to reach for any point in this region. And in this case, it shows to have a probability to transition between S3 and S4 that is 0. This means that it's now possible for the MDP to reliably draw conclusions about how to move between different regions. So how do we make sure that our inverse models are consistent? So for example, assume that we have a data set to S3 in this case. The yellow postures here are the postures that we have already seen. What we want to do is that we only want to add new postures if they are consistent with the postures that we have already seen. So how can we know if a posture is consistent or not? A first observation is that when we try to go to a region, we will use linear regression using the postures already seen there. This means that if you try to go to a region and also end up in this region, then the posture you have has to be consistent because this posture was generated by the postures already seen in this region. So the conclusion is thus that if you try to reach region S3 and you actually end up there, then you know that your data point is consistent. So the way we solve this problem is that we will only add new samples when they are result of a successful transition, or if you reach a region for the first time, because in this case, then you know it has to be consistent. Okay, so how did we evaluate this? So we set up an experiment with a high-dimensional arm in a restricted environment. And the rules for this environment is that the arm can't move through walls, it cannot move through itself. It also has a restricted speed, which means that it cannot move infinitely far in this environment in one iteration. The goal now is to see if the addition of a higher planning module will allow it for more efficient control in this complex environment. Okay, so first I want to show you the results when we didn't allow any higher level planning. In this case, you only have one state, which means that this is traditional goal babbling basically. The blue dots you see are random goals in the task space that are set out for the arm to try to reach. And each time the arm gets stuck, goes into itself, or reaches its goal position, then a new goal will be set out somewhere. Okay, let's jump to the evaluation of this. So the goal now is for the arm to reach for the red cross that we put in different positions. And as you can see here, it will try to go straight to the red cross, which would make it end up into the walls most of the times. And it doesn't mean that the inverse model is bad. Often it would actually end up pretty close to the exit it was allowed to if it could go through the walls. But since it cannot plan its trajectories, it's really hard for it. Okay, let's see what happens if we introduce some segmentation to this space and allow some MDP planning on top. So in this case, you have a 6x6 segmentation, and the colors you can see now shows how many times a certain region have been visited. A goal region is now selected by the MDP planner in the regions where the arm think it will learn the most, and then the blue goal is placed randomly within this region. Okay, so now let's look at the evaluation. Once a final goal is set out, then the agent will choose what regions to reach next, and it will place a blue goal in it. If the agent for some reason fails to go where it tries to go, it might bump into a wall or something, it will directly try to reposition itself within its current region. Okay, as you could see, it was able to move around more or less to any position in this space. So let's have a look at the results. First of all, we wanted to see the effect of different resolutions or segmentations of the task space, and especially we wanted to compare what would happen if you couldn't plan at all, like in the case if you have a 1-by-1 segmentation. And it's also interesting to see what would happen if you have regions that have walls going straight through them, like in the case of 7-by-7. So here are the results. On the y-axis, you can see the reaching error, which is that if the arm would start in a random position with its end effector, and it's asked to go to another random position in its task space, how close to this goal would it generally end up? In the background here, you can see the distribution of different reaching errors, and the red lines are the geometrical mean of these outcomes. In the goal babbling case, in the 1-by-1 segmentation, you can see that it's not actually making that much of a progress. And the reason for this is that it always bumps into the walls, even though the inverse model might actually be very good, and we also proved that the inverse model did improve a lot. But what you can see when you add this planning capability, the agent very fast learn how to avoid the basic walls, and you would have a much better performance. When we compare the different segmentations to each other, it seems like the higher resolution you have, the better, but this can only be true up to some point, because the higher resolution you have, it also means that you will have a bigger MDP, which means that you would need more time to learn this MDP. But it seems like 10-by-10 is not big enough for this effect to start to show up. What is interesting is that 7-by-7 went pretty well, as well as 6-by-6. And when we evaluated this, it seems like the agent is basically just trying to avoid the regions with walls between them. We also wanted to evaluate the effects of different degrees of freedom for the arm. So in this case, for example, you can see a 5 degrees of freedom arm and the 100 degrees of freedom arm. So we tried different degrees of freedom between 5 degrees of freedom and 200 degrees of freedom. And what is interesting here is that it doesn't really matter. This method, just like goal babbling, is more or less indifferent to the degrees of freedom, which is pretty nice, and it also shows the strength of goal babbling frameworks, that it's not interesting how big the model space is, because it is the task space that you try to cover. So, what are our conclusions? The conclusions are that finite element goal babbling successfully combines MDPs with a goal babbling framework. It can handle environments where planning is necessary, and it's more or less indifferent to the degrees of freedom of the arm. So that was our presentation, and if you want to find more information, you can go to pontusloviken.com/ICDL-Epirob-2017. Thank you.